Hello, I've had a query about this particular question from the homework, and I'm not surprised, because in order to make sense of this question, you need to know something I haven't taught you, namely the chain rule for differentiation. So I'm going to give you a very quick introduction to the chain rule for differentiation, and then show you how it applies to mechanics questions of this type. Look at this function here. What we've got here is a function inside another function. We've got something cubed, but the thing we are cubing is a bit complicated. It's not just an x or a z or something. What we're looking for here is dy by dx. There are two ways we can do this. The first way, using techniques you already know. First of all, we expand this bracket here. Well, it's a bit ugly, but not so bad. It's only a cube. And if we expand that using Pascal's triangle, we get this. And then we can simplify that, and then we can differentiate that term by term to get the following derivative. There is another way of doing this which does not involve expanding those brackets. It works like this. Let's imagine our original function as y equals u cubed. U is another function of x, so we'll write that down separately. Here, we are going to work out dy by du, not dy by dx. Well, that's really easy. Meanwhile, over on the right here, we can work out du by dx, which is also pretty easy. Now, this dy by du equals 3u squared thing really means, because that's all u is. And we've still got this du by dx thing here. I'm going to look at what happens if I multiply this thing by that thing. Okay, first thing we have to do, square out this. Now, I'm going to multiply out my two brackets, that times that, 3 terms times 2 terms. Then I'm going to collect up terms. And finally, I'm going to multiply out this bracket. Does that look familiar? Well, it should, because that is exactly the same as that. In other words, dy by du times du by dx is the same as dy by dx. And this always works. It's almost as if those du's kind of cancel out. Well, they do kind of cancel out, but please do not conclude from this that derivatives are fractions. They are not. But this is what we mean by the chain rule for differentiation. Dy by dx is equal to dy by du times du by dx, and this is the way we differentiate functions of functions. Right, let's go back to the question we started off with. We have a particle of mass m starting at point A. It's heading towards point B. We know that at the initial position it has velocity 3 meters per second, and once it has moved 2 meters, it has velocity 5 meters per second. Let's see what we can do with this information if we start applying the chain rule. Favourite formula in all of physics, F equals ma. Now we know that acceleration is just rate of change of velocity. So we can rewrite that as m dv by dt. And according to the question, this force here is mkx. Oh, that's good. The m's cancel out. And we get dv by dt equals kx. Well, that's all very well, but this question says nothing at all about t. We don't know anything about the times in this motion. This is where the chain rule comes in. And this is a very, very widespread application of the chain rule in mechanics. Acceleration is dv by dt. But according to the chain rule, that is equal to dv by dx times dx by dt. Hang on. This second derivative here, dx by dt, is just the velocity. Oh, look, acceleration is v times dv by dx. We've suddenly taken t out the whole equation. So we can now rewrite this equation here as v dv by dx equals kx. This thing here is what we call a differential equation. Oh dear, something else you've never done. I'm now going to show you how you deal with this using techniques you already know, but probably haven't thought about using in this way. I have an equation there. It's an equation, so I can just deal with it by doing the same thing on both sides of the equals sign. I'm going to integrate both sides of that equation with respect to x. And I get that. Oh my goodness, those dx's sort of cancel out again. In fact, we can do that. Now we simply have to integrate v with respect to v and kx with respect to x. Well, the integral of v is just a half v squared, and the integral of kx is a half kx squared. Now remember, when we integrate, we always have a constant factor, a c we have to add on. Now, if you wanted to be really pedantic, you'd say, well, we have to add a c on this side and then a different c on that side, maybe c dashed. In practice, it's much simpler just to add it all on one side. So I now have an equation connecting v and x. I also have some information about v, my velocity, and x, my horizontal displacement. We call this information we have here the boundary conditions of our differential equation. And we have two separate bits of information here. The first bit of information we have is that at A, where displacement equals 0, velocity is 3. Okay? So first of all, we have at x equals 0, v equals 3. Let's sub those values into this equation. Oh, well, that's just 0. So we end up with 4.5 equals c. Great. We also have another boundary conditions at 2 meters. 2 meters displacement, we have a velocity of 5 meters per second. Sub it in again. That gives us, oh look, 12.5 is 2k plus 4.5, 2k is 8, k is 4. So this whole equation here becomes 1/2 v squared equals half of k, that's a half of 4, 2x squared plus 4.5. So find the distance of this particle from A when it attains a velocity of 9 meters per second simply means substitute in 9 for v and work out x. And if you figure that out, you will get x equals the square root of 18, which is about 4.24 meters. There you are. Job done. But it does require both the chain rule for differentiation and solving a differential equation. Sorry about that.